Part 2. Argument. Directions. Closely read each of the 4 texts provided on pages 11 through 17 and write a source-based argument on the topic below. You may use the margins to take notes as you read and scrap paper to plan your response. Write your argument beginning on page 1 of your essay booklet. Topic. Could algae be the solution to our energy problems? Your task. Carefully read each of the 4 texts provided. Then, using evidence from at least 3 of the texts, write a well-developed argument regarding whether or not algae could be the solution to our energy problems. Clearly establish your claim, distinguish your claim from alternate or opposing claims, and use specific, relevant, and sufficient evidence from at least 3 of the texts to develop your argument. Do not simply summarize each text. Guidelines. Be sure to establish your claim regarding whether or not algae could be the solution to our energy problems. Distinguish your claim from alternate or opposing claims. Use specific, relevant, and sufficient evidence from at least 3 of the texts to develop your argument. Identify each source that you reference by text number and line numbers or graphic, for example, text 1, line 4, or text 2 graphic. Organize your ideas in a cohesive and coherent manner. Maintain a formal style of writing. Follow the conventions of standard written English. The texts. Text 1. Biofuel from algae, Part 1. The pros and cons of pond scum. Text 2. Algae's potential as a transportation biofuel. Text 3. Green oil. Scientists turn algae into petroleum in 30 minutes. Text 4. Green crude. The quest to unlock algae's energy potential. Text 1. Biofuel from algae, Part 1. The pros and cons of pond scum. As we approach a point of peak oil, the point at which fossil fuels become scarcer and more expensive, and some argue that we've already passed that point, the interest in biodiesel has been revived. Producing fuel from food products, however, has been morally controversial from the beginning. As the planet's population and demand for food grows, it becomes more unconscionable, and unconscionable means unethical, for the wealthier nations to waste food products like corn, soy, sugarcane, and rapeseed, as well as food cultivation space, on filling their gas tanks. To mitigate, or make less severe, wasted food and wasted land, in recent decades, there has been rising interest in cultivating biofuel from algae. To pursue a better promise of low-cost, scalable, in other words, capable of being easily expanded on demand, green and clean biodiesel, research organizations and institutions, both private and public, have sunk a lot of time and money into algae research in an effort to advance a technology that could produce transportation fuel on a large scale. It simply makes sense. As anyone who has ever had a fish tank knows, algae is ridiculously easy to grow. There are many kinds of algae, complicated multicellular forms, think seaweed, as well as simple single-celled forms, think pond scum. It's hardly a fussy plant, and producing large quantities of it doesn't exactly require a green thumb. What's so compelling about algae is that it contains a high amount of fatty molecules that are similar to vegetable oils, and these fats can be rather easily converted to a biofuel that can act as a drop-in replacement for petroleum-based gas, diesel, and jet fuel. The pros of algae-based biofuel. One of algae's major attractions is that unlike corn for ethanol or soybeans for biodiesel, algae can be grown in places unsuitable for food cultivation, which takes away the wasted space drawback by making use of non-arable, or not suitable for growing crops, nutrient-poor land that won't support conventional agriculture. Algae can be grown in ponds, tubes, or even large bags provided it gets the right combination of vitamins, minerals, and sunlight. It doesn't require soil or even fresh water to grow, and when cultivated in large quantities, algae can produce more energy per acre than any land crop, making it the most energy-efficient plant for biodiesel production. Far more efficient than corn, sugarcane, or soy. And unlike row crops, which are dependent on growing seasons, algae can be grown at any time of the year since ideal growing conditions can be easily simulated. In addition, it requires no fresh water for irrigation and no application of petroleum-based fertilizers. Algae can thrive in desert ponds using high saline water from aquifers that can't be used for traditional crops. Many species of algae can even grow in wastewater from treatment plants and water that contains nitrates, phosphates, and other pollutants. In fact, algae ponds and cultivation facilities are often located as close as possible to wastewater or pollution sources, since algae thrives on both carbon and bacteria. The cons of algae-based biofuel. While algae-based biofuel may use far less land and have a higher energy yield than other biodiesel crops, its production also requires more energy and water, albeit not necessarily fresh water, than plant sources such as corn. It also has higher greenhouse gas emissions. The reason is that the production of the final product is more complex and therefore more energy intensive. While many kinds of algae are easy to cultivate, the species of the plant that contain the most fats are most suitable for biodiesel, and these specialized lipid producers are a bit fussier than ordinary algae. The cultivation of algae, like the cultivation of most other plants, requires large amounts of phosphorus as a fertilizer. And while it's not an oft-discussed topic, the world is currently on the brink of a peak of availability of Earth's finite phosphate resources. Peak phosphorus, as it's called, is the point in time at which the maximum global phosphorus production rate is reached. According to some researchers, Earth's phosphorus reserves are expected to be completely depleted in 50 to 100 years, and peak phosphorus will be reached by the year 2030. This is a fairly scary prospect for global agriculture, not just for algae production. To succeed, large-scale algae production will need to reduce its use of phosphorus and find ways of reusing what it does require. The need for phosphorus in cultivation has been called by Forbes magazine the Achilles heel of algae biofuel. Written by Tracy Shelmetick. Excerpt and adapted from Biofuel from Algae Part 1, The Pros and Cons of Pond Scum, from newsthomasnet.com, February 19th, 2013. Text 2, Algae's Potential as a Transportation Biofuel. Algae can be converted into various types of energy for transportation, including biodiesel, jet fuel, electric power, and ethanol. The potential advantages of algae-based biofuel over other biofuel pathways include higher biomass yields per acre of cultivation. Biomass is organic matter used as a fuel. Little to no competition for arable land, arable meaning suitable for growing crops. Use of a wide variety of water sources. The opportunity to use carbon dioxide, CO2, from stationary sources. Stationary sources are sources that emit a certain amount of pollutant as defined by the U.S. Environmental Protection Agency. And the potential to produce drop-in, ready-to-use fuels. Potential drawbacks include the anticipated cost of production, the amount of resources, that is water and land, required to produce the biofuel, and the lack of commercial-scale production facilities. Algae-based biofuel research and development are in their infancy, although work has been conducted in this area for decades. At present, published research efforts offer policymakers little guidance on what algae types or conversion methods could be the front runner for commercial production, or on when and for which biofuel. Potential challenges. The primary challenge for ABB, agriculture-based biofuels, is that it has not yet been demonstrated to be economical at commercial scale. If economic production can be achieved, the potential impact on the national transportation fuel network would need to be assessed. Also, as mentioned above, algae cultivation requires significant amounts of CO2, and there are questions about where the CO2 would come from. While the CO2 could come from existing stationary sources, it may be incorrect to assume that all algae processing facilities would be located near existing sources of CO2, or that enough CO2 from existing sources would be available to meet demand for commercial levels of ABB production. It is likely that siting and permitting of these facilities would require involvement of local, state, and federal government agencies. It is unclear how use of CO2 from a power plant for the production of algae would be treated under the Clean Air Act. There may be supply and demand concerns for ABB. The use of some feedstocks for biofuels has been controversial, as some report that rising demand for biofuels shifts biomass feedstocks and arable land away from use for other purposes, like food. Some assert that significant quantities of resources, like land, water, and CO2, exist to support algae-based biodiesel production. However, it is not clear if existing resources can support biodiesel and biojet fuel, bioethanol, and more from algal feedstock. The National Research Council, NRC, reports that the quantity of water necessary for algae cultivation is a concern of high importance, among others, that has to be addressed for sustainable development of ABB. In general, biofuels derived from open pond algae production consume more water for feedstock production and fuel processing than petroleum-derived fuels, although the water quality may not be comparable since some algae is able to use waste or brackish water, brackish being salty. One reported possible technique to drastically curb water use is to site ABB facilities at optimized locations where land with the lowest water use per liter of biofuel product produced is available, but algae would still use significantly more water than petroleum. Another technique is to use water unsuitable for other purposes. Algae requires both water and nutrients, like phosphorus, to grow, which may inadvertently, that is accidentally, put it in competition with other areas of agriculture, depending on water sources and land types selected for algae cultivation should ABB be produced at a large scale. Also, large-scale ABB production may involve the use of genetically modified algae, which some may oppose because of concerns that genetically modified algae may escape into the environment and become invasive as algae that are non-native to that location. Article is by Kelsey Brackmort, excerpted and adapted from Algae's Potential as a Transportation Biofuel, Congressional Research Service 7-5700, wwcrs.gov, January 30th, 2014. Text 3. Green oil. Scientists turn algae into petroleum in 30 minutes. Scientists at the Pacific Northwest National Laboratory, or PNNL, are claiming success in perfecting a method that can transform a pea-soupy solution of algae into crude oil by pressure cooking it for about 30 minutes. The process, called hydrothermal liquefaction, also works on other streams of organic matter, such as municipal sewage, and the crude oil created is lightweight and low in sulfur and can be dropped in to refineries that process fossil crudes. Fossil crudes are unrefined oil and natural gas. It's a bit like using a pressure cooker, only the pressures and temperatures we use are much higher, said researcher Douglas Elliott in a statement. In a sense, we are duplicating the process in the earth that converted algae into oil over the course of millions of years. We are just doing it much, much faster. It only makes sense that scientists should be able to figure out how to turn algae into crude oil. After all, most of the oil that we drill out of the ground was formed by algae and other seaborne flora that piled up at the bottom of the ocean over millennia, then got compacted and heated over eons and transformed into petroleum. Flora are plants. But figuring out how to do it economically is a challenge. A half-century ago, researchers were growing algae on the roof of MIT. More recently, ExxonMobil raised hopes of algae-to-oil crowd in 2009 when it forged a research venture with Craig Venter's Synthetic Genomics. If Venter, who was first to decode the human genome, could find or engineer an algae strain adept at naturally creating oils, Exxon would fund development to the tune of $600 million. Unfortunately, Venter called off the quest a few years later. Algae just weren't oily enough to be commercially viable sources of crude. Given 100 pounds of algae feedstock, the system would yield 53 pounds of biofuel, according to the PNNL studies. The oil is chemically very similar to light, sweet crude, with a complex mixture of light and heavy compounds, aromatics, phenolics, heterocyclics, and alkanes in the C15 to C22 range. Not all the organic matter gets turned into oil. It also yields a stream of carbon dioxide, hydrogen, and oxygen, which can be readily turned into a stream of synthetic natural gas and burned to generate heat or electricity. Also left over is water rich in plant nutrients, nitrogen, phosphorus, and potassium, previously present in the algae. This water can be sold back to the algae ponds as fertilizer. Not having to dry the algae is a big win in this process. That cuts the cost a great deal, said Elliott in a statement. Then there are the bonuses, like being able to extract usable gas from the water and then recycle the remaining water and nutrients to help grow more algae, which further reduces costs. The researchers figure that at current algae prices of several $100s a ton, they could make algae-based fuel for the gasoline equivalent of less than $5 per gallon. And algae is only the most viable oil source. The same tricks can oilify all sorts of other organic waste, such as manure, municipal sewage, vegetable compost, even fish heads. Indeed, if the technology can be successfully scaled up to commercial size, says Genefuel CEO Jim Euler, our stinky streams of human waste alone could provide the feedstock to meet 10% of our worldwide petroleum demand. The key will be in figuring out how to make massive quantities of algae cheap. Because then, explains Euler, the rest will support itself, excluding the energy used in growing the algae, a huge caveat, or warning. The hydrothermal extraction process developed at PNNL can create about 9 units of energy for every unit used. No doubt algae cultivation will improve. Until then, the big hope for this technology now may be to pair it with a feedstock that cities otherwise have to pay to get rid of, like sewage. Euler envisions a distributed system of hydrothermal liquefaction systems set up at regional sewage plants and a fleet of trucks that come to load up on crude oil once a week. That article was written by Christopher Hellman, excerpted and adapted from Green Oil, Scientists Turn Algae into Petroleum in 30 Minutes, from www.forbes.com, December 23, 2013. Text 4. Green Crude, the quest to unlock algae's energy potential. Although scientists and entrepreneurs have been trying to unlock the energy potential of algae for more than 3 decades, they don't yet agree on how to go about it. Some companies grow algae in ponds, others grow them in clear plastic containers, and others keep their algae away from sunlight, feeding them sugars instead. To improve the productivity of the algae, some scientists use conventional breeding and others turn to genetic engineering. Algae is the most promising source of renewable transportation fuel that we have today, says Steve Kay, a distinguished professor of biology at the University of California, San Diego, and co-founder of the San Diego Center for Algae Biotechnology, a partnership of research institutions, business, and government. And yet there's plenty of reason for skepticism about algae. Scientists and entrepreneurs have been trying for decades to unlock algae's energy potential with mixed results. After the 1970s oil shocks, the U.S. government created an algae research program that analyzed more than 3,000 strains of the tiny organisms. The program was shut down in 1996 after the Department of Energy concluded that algal biofuels would cost too much money to compete with fossil fuels. A decade later, after President George W. Bush declared that the U.S. is, quote, addicted to oil, government research into algae was restarted, and venture capital flowed into dozens of algae startups. Oil companies ExxonMobil and Chevron placed bets too. But algae companies haven't made much oil yet. Sapphire's annual production targets of 1.5 million gallons for 2014 compares to the U.S. daily oil consumption of 18.8 million barrels. Even algae's most enthusiastic advocates say that commercialization of algal biofuels on a scale that would matter to the environment or the energy industry is at least 5 to 10 years away. High costs remain the big obstacle to commercial production. The algae business has suffered from fantastic promotions, bizarre cultivation systems, and absurd productivity projections. says John Benneman, an industry consultant and PhD biochemist who has spent more than 30 years working on algae. Even if the capital costs and operating costs of algae farms are low and the productivity of the algae is improved, Benneman says that algae biofuels cannot compete with fossil energy based on simple economics. The real issue is that an oil field will deplete eventually, while an algae pond would be sustainable indefinitely. In a thorough 2010 technology assessment, researchers at the Lawrence Berkeley National Laboratory estimated that producing oil from algae grown in ponds at scale would cost between $240 and $332 a barrel, far higher than current petroleum prices. Perhaps more worrisome, government scientists say the environmental benefits of algae remains unproven. Writing in American Scientist, Philip T. Pienkos, Liev Lorenz, and Andy Aden, all of the National Renewable Energy Laboratory, say that the few life cycle assessments of algae done so far have shown unpromising energy returns and weak greenhouse gas benefits. By phone, Pienkos acknowledged that in theory, algae should produce low-carbon fuels because the CO2 emitted when the fuels are burned is absorbed from the air when the algae grow. But, he says, calculating the true sustainability benefits of algae requires doing a detailed study of inputs and outputs, and that will be difficult until big algae farms are built. That article was written by Mark Gunther, excerpted from Green Crude, The Quest to Unlock Algae's Energy Potential, from e360.yale.edu, October 15th, 2012.